Okay guys, we're going to talk a little bit about intermolecular forces, and this might be a little bit of a long video, but I think it's important because it really gives you a lot of information about liquids. So this whole chapter is about liquids and solids and the different phases, and we've spent a lot of time on solids, and now we're going to get into liquids a little bit more. And to understand liquids, you have to understand intermolecular forces. So intermolecular forces, or IMFs, as they're commonly referred to, not to be confused with Impossible Mission Force. If you're a fan of Mission Impossible, don't confuse the two. So intermolecular, inter meaning between, molecular, between molecules. These are the forces between molecules that cause attraction. Okay, so intermolecular. So we're talking about more than one molecule. We've talked about bonding, of course, which is the attraction between two atoms that allows for a chemical bond to occur. Intermolecular forces is kind of the stickiness between molecules that keeps them held together. So we usually refer to this as stickiness, in the sense of like cookie dough. If I have two balls of cookie dough and I throw them together, then they stick to each other, as opposed to two pool balls, like a cue ball. If I hit the white cue ball and I hit a pool ball, then they don't stick together. One hits the other and the collision is elastic. All the energy is transferred from one to the other. Now this is usually caused, the stickiness and the attraction is caused because of the attraction between opposite charges. And usually here we're not talking about full charges. We're not really talking necessarily about ions, although we can talk about some intermolecular forces that involve ions. But if we're just talking about between liquids, then we're talking about opposite partial charges. So we'll be talking about things like polarity, for instance. So let's start there. Let's start at the top. There's basically three major types that we're going to be talking about. And we'll kind of start in the middle, and then we'll get to the stronger and the weaker ones. So the first of the three types is dipole-dipole. Dipole-dipole. So dipole-dipole, remember dipole moments are only on polar molecules. So a dipole-dipole attraction is between two polar molecules with dipoles on them, and the partially positive side of one molecule is going to be attracted to the partially negative side of the other. Let's take hydrochloric acid, for instance. If we take HCl, this bond between hydrogen and chlorine, if we go to our table of electronegativities, which I happen to have one right here, if we look at hydrogen, hydrogen is 2.1, chlorine is 3.0. So 2.1, 3.0. The difference between the two then is 0.9, which puts it in the polar range. If I draw the dipole on this, it's going to point towards the chlorine, meaning that I have a partial negative here and a partial positive here. Okay, so that's a little bit of review from what we've talked about before. If I have multiple HCl molecules together, then they're all going to have this dipole that points in the same direction. There'll be a partial positive on the one side, partial negative where all the electrons are hanging out on the more electronegative chlorine. Now this attraction then between the partially negative side of one molecule and the partially positive side of another molecule, this attraction right here is a dipole-dipole moment. Okay, so this is dipole-dipole, the attraction between two polar molecules. They don't have to be the same molecule. This is just one particular example. And again, this stickiness or attraction between them comes because of the attraction between opposite charges. So that's the first of our three types of intermolecular forces. The second is a specific type of dipole-dipole, which is called hydrogen bonding. And I mentioned it briefly when we talked about water. I usually will shorten this down to H bonding, just so that you know my shorthand here. So hydrogen bonding is a specific type of dipole-dipole attraction. And we usually associate it with water. When you talk about water and how cool it is, which I've sort of scratched the surface of in this class, then you can attribute a lot of the cool stuff that water does to hydrogen bonding. Okay, so hydrogen bonding is the specific dipole-dipole between two water molecules, if we want to use that as a specific example, and then I'll give you a more general definition once we get this all put together. Okay, so we know that the bond between oxygen and hydrogen is polar. If we weren't sure, we could go back to our electronegativities and check to make sure. Oxygen is 3.5, hydrogen is 2.1, so yes, it's a polar bond. So the partially negative oxygen and the partially positive hydrogen are attracted to each other, right? Opposites attract. So this is our not only dipole-dipole, but also our hydrogen bond. And hydrogen bonding occurs between a partially positive hydrogen on one molecule, so this is one molecule over here, and a negatively charged, partially negatively charged oxygen, fluorine, or nitrogen on a second molecule. So this is molecule 1 over here. This means that this is a polar bond, since this is a partially positive hydrogen. And this also has to be a polar bond for my oxygen to be partially negative, a polar bond for my fluorine to be negative, or a polar bond for my nitrogen to be negative. So the attraction between a partially positive hydrogen on one with a partially negative oxygen, fluorine, and nitrogen on a second molecule is hydrogen bonding. So it's very specific. It has to be these three elements. So let's go back to our dipole-dipole example. So if we look at HCl here, we have these two HCl's that are attached or attracted to each other because of these opposite charge. So again, stickiness. This is not considered hydrogen bonding. Even though it has a hydrogen in it that's partially positive, it's not attracted to an oxygen, fluorine, or nitrogen. So this is not hydrogen bonding. So that's the distinction there. And the reason that we make this distinction is because hydrogen bonding is a really strong intermolecular force, the strongest, in fact. When I said I was going to start in the middle, it's because dipole-dipoles tend to be somewhere in the middle. Strongest being hydrogen bonding, dipole-dipole just in general, a little less strong. And then the least strong, or the weakest, is our third, which are van der Waals forces. Now you should recognize van der Waals because he was the one who was looking at real gases as opposed to ideal gases. So van der Waals forces are kind of related to this idea that there are specific things about particles that allow them to behave in specific ways. And they are the weakest of the IMFs, like I mentioned. And they happen because of random motion of electrons. So, if we take something that's generally considered to be nonpolar, like something that is paired with itself, right? If something is paired with itself, then it's going to be sharing electrons equally. And so in this cloud, then, we have a kind of an even distribution of electrons. That's the way that we've talked about our model. So this is diatomic chlorine, if we're thinking about it that way. But at any given time, there is a probability, a non-zero probability, that all of the electrons are clumped up on one side or clumped up on the other. So there's a probability, and I'm just going to call it clumping of electrons, which isn't necessarily a scientific term, but you kind of know what I mean. These electrons are in random motion. That's what kinetic molecular theory tells us. So at any given time, there could be a shift in this cloud. So it could look something like this, where we have these chlorines and maybe there's a little more of a bulge over here, a little less electrons over here. So now we have more electrons over on this side, leading to a slight negative charge with that extra electron density. That means there's slightly less over here, right? This is just randomly occurring. It's not going to stay this way. It's going to even out overall. If we're talking about on average, it's going to look more like this than it does like this. But at a given second, it could look like this. And when it does, then if there's another diatomic chlorine that's next to it, or any molecule for that matter, if this large extra bulge of electrons interacts with the electrons on this one, then like charges are going to repel each other, right? So my electrons on this one and my electrons on this one are not going to want to interact. So if this one bumps into this guy, then that's going to push the electrons on this one away from wherever the collision occurs. So this one's running into this one here, and that shifts the electron cloud like this. And now there's this slight discrepancy on this molecule as well. So now there's a slight negative charge on the one side, a slight positive charge on the other side, and we call this process right here an induced dipole. An induced dipole is a dipole that is induced or forced where there isn't normally one. And then once we have this kind of differential here, so there's this slight negative charge on this molecule that induced this slight positive charge in this one, now there's going to be a slight attraction or stickiness between the two sides of these molecules, okay? And this is a van der Waals force. So this is just because of the random motion of electrons, it induced the dipole, and now there's an attraction from these partial charges. Now this occurs in everything. So everything has van der Waals forces, but it's kind of the most interesting in molecules that don't normally have dipoles. So in non-polar molecules, it's the only force. So the reason that nonpolar molecules in liquid form like to interact with each other at all is because of the van der Waals forces. Okay. Now this can also occur in individual atoms, and this kind of gets us into the noble gases. There is an attraction between noble gases with themselves. If you take argon, for instance, if we're visualizing the electron cloud, we know that the electrons are in orbitals. We know that the electrons have specific energy levels associated with them. But if we picture these electrons on argon at any given time, because of the random motion of electrons, there's going to be a couple that are around, right? But there's nothing to say that at any 1 second there's a cluster of electrons on this side of the atom. And that would give a slight negative charge on that side. And where there are fewer, it would be a slightly positive charge. There's a deficiency of electrons there. And if we have a bunch of argon atoms that are doing this, then this could kind of induce, now this isn't so much a dipole, although sort of, you're talking about two poles of one atom then. But we could have some cluster of electrons on this argon, and that leads to a slight negative charge here and maybe a slight positive charge here, and then this stickiness that results from this uneven distribution of electrons is still a van der Waals force. Okay, so it's kind of a weird thing to think about. Now the strength of these attractive forces, so we kind of introduced the three, the strength of the attractive forces impacts different properties, again, specifically in liquids. So I want to talk about those briefly. I'm going to talk about how the strength of these IMFs actually impacts the properties of these liquids, and then I'm going to talk about how you determine which IMFs are present in any given sample. So the first property that it impacts is viscosity. And again, we're focusing mainly on liquids, but this can also be seen in gases that are non-ideal, and it can also be seen in some solids. I mean, not viscosity, obviously, but some of these other ones. So viscosity is how resistant a liquid is to flow. So we said that liquids are fluid and the particles can move past each other, and so that allows for this fluidity of liquids. But viscosity is how resistant then that liquid is to flowing. So think maple syrup, think honey, think tar, all these things that are viscous. Okay, so if you increase the attractive forces or you increase the strength of the IMFs in that liquid, then you're increasing the attraction of the molecules to each other. Then what do you think that's going to do to the viscosity? If I increase the strength of the attraction of the liquid to itself, do you think that's going to increase or decrease the viscosity? And you should say that it's going to increase. If I have really strong attraction to myself as a liquid, then I'm going to want to stick together. That means that I'm not going to want to run around too much. So the less viscous the material, then it tends to have fewer IMFs. Or if it isn't that viscous, then it also has other things going on. But this is just one way to predict whether or not a liquid will be viscous. Another characteristic that's impacted by these IMFs is boiling point. The boiling point is the temperature at which something boils. It's also the point where the vapor pressure is equal to the atmospheric pressure. So I'm going to say P atmosphere is equal to P vap, right? So the vapor pressure, or the partial pressure of the gas over that liquid, is equal to the atmospheric pressure. At that point, then the liquid starts to boil. So let's think about this in terms of IMFs. If I increase the strength of my attractive forces, so I have really strong attraction between my particles and my liquid, do you think that's going to increase or decrease the boiling point? And hopefully you said again, it's going to increase the boiling point, meaning that the temperature that is required to heat this thing up to a boil is going to increase. It takes more energy to do that because I have such a strong attraction between my molecules. Okay, and we can relate this also to vapor pressure. So if you increase the vapor pressure, remember that the vapor pressure is the pressure that's exerted by the vapor over the liquid. So we have some evaporation of the liquid into the gas phase or in the vapor phase, and then that vapor exerts pressure down on the liquid that it's over. So if we increase the pressure that's over the liquid, do you think that's going to increase or decrease the boiling point? So we put more pressure on that liquid, that's going to make it harder for the gas particles to leave. So if we increase the vapor pressure, or if we increase atmospheric pressure for that matter, then that's going to increase the boiling point. It takes more energy to overcome that extra pressure from the vapor. Now if we think about this in terms of position, when you go up in altitude, you have less pressure above you, less atmosphere above you. So when you increase your altitude, you decrease your atmospheric pressure. Right? Are you with me on that? So 1 atmosphere of pressure is literally how much atmosphere you have over you at a given time. So if you get up in altitude, whether it's in a plane or on a hill, then now you have less atmosphere over you. And if I decrease my pressure, then I should also decrease my boiling point. And we find that to be true. If you've ever heard of people camping and they go up on mountains, for instance, then that changes the boiling point of water if they're cooking. So if we take water, for instance, at sea level, we know that the boiling point of water is 100 degrees Celsius. Okay, so we know that that's true. That's our guesstimate on average for water anyway. If you were to go up in altitude, let's say to Snoqualmie Pass, which is covered in snow today, so you probably wouldn't want to do that. But if you went on the top of Snoqualmie Pass, then the change in the altitude would cause water's boiling point to decrease to 96.3 degrees Celsius, which doesn't feel like a huge difference, but it means that much less energy that you have to put in to heating up the water to a boil. Now, just as an aside, and I just wanted to kind of put this in your notes because I think it's important. This is probably something that you know intuitively. But we talked about the different energies that go into changing phases, and we said the enthalpy of vaporization, or the heat of vaporization, is the amount of energy it takes to go from the liquid to the gas phase. Now, this heat of vaporization is always going to be larger than the heat of fusion. Remember that this is the enthalpy of fusion, which is the amount of energy that it takes to go from a solid to a liquid. Okay, so always this heat of vaporization is going to be larger. And you can think about that in your experience with water. So if we think about solid water melting into liquid water, I could have an ice cube out right now, and I put my ice cube out and it would melt into liquid water right in front of me at room temperature. But I have to put a lot of energy in. There's a big difference between putting the ice cube out and it melting versus the amount of time it takes to go from a liquid to a gas phase. I have to put a lot of energy in order to get it to boil, right? In order to get it to evaporate. So this is something that you've seen and experienced, but that's true for all substances. Okay, so another characteristic or another property of liquids that's impacted by these IMFs is surface tension. It's fun to talk about liquids because we already know a lot of these things. These are things that we've seen or experienced in everyday life. So surface tension is kind of the elasticity of the surface. Okay, and we can picture this with water particularly, but let's think about this in terms of IMFs. So here's my surface tension. If I increase the strength of my IMFs, do you think that's going to increase or decrease surface tension? So am I more likely to have a stronger surface tension if I have greater IMFs or lesser IMFs? And hopefully you're saying greater. If you increase the attraction between the particles, then you're increasing the surface tension. You're increasing how much it's attracted to itself. So if we have water, for instance, again, water's kind of my go-to on a lot of these. If you have a piece of wax paper or like a leaf, for instance, and you put some water in there, it's going to bead up, right? So you have this little droplet of water and you can kind of move it around, and that's kind of fun. And the reason for that, the reason that it beads up on some surfaces anyway, so let's say it's waxed paper or waxiness on a leaf, and we'll talk about in the next chapter why this occurs. But if we have water on waxed paper here, then it's going to cause this little droplet. And the reason that it causes this droplet is because all of the water molecules are attracted to themselves. So they kind of circle in on themselves. And we call this cohesion or stickiness to self. And high cohesion leads to high surface tension, and this is part of the reason that it hurts so badly when you belly flop into a pool, right? You belly flop into the pool and then your whole body is red because you had to break the surface tension. This is also the reason if you have a glass of water, so here's my glass, and then you pour your water into it, you can fill it to the point where the water comes over the level of the glass, right? So here's my water, it's right there on top. If I was kind of blowing up that, here's the surface of my glass, and here's my water over it, and so it's not quite overflowing, it's not quite spilling because of this little lip of water. So this is the surface tension, right? If I didn't have any surface tension, if I overfilled it, all of this liquid would come out of the glass and it wouldn't hold like this. This is also the reason that we can have like, you know, those bugs that are skippery, kind of skipper bugs. And so the skipper bugs can be on the surface of the water like this for that reason. Okay. Another thing you can do, which is kind of fun, is you can put a paper clip and actually balance a paper clip. If you do it right and you have a little bit of patience, you can balance a paper clip on the surface of water and just see the indent there. And that's because of the high surface tension, the high intermolecular forces that exist in water. Now, another cool thing about surface tension and water in general is it allows for an effect called the capillary effect. We've now played with capillary tubes in lab a couple different times, and you found that, here's my droplet of water again, you put that little tiny tube into a sample that's water-based, right? And you have this tiny little tube, and you find that the fluid in there is sucked up. So you just tap it to the water itself, and then it is sucked up the tube. That's the capillary effect. And this is basically defying gravity, right? The liquid is moving in opposition to gravitational pull, which is trying to pull down. So here's gravity trying to pull down, and the liquid is moving despite of that. So we said that cohesion is stickiness to itself, and it and adhesion account for this capillary effect. So adhesion is stickiness to other. Okay, and by other here I just mean to other surfaces, specifically for, in the case of water, something like glass or plastic. Okay, so it works something like this. If I was to blow up this tube so that you could kind of see what was going on in the walls, when you put it into the water right away, then it's going to be here. And the water, because of adhesion, is going to be attracted to the sides of the tube. So attraction to other is adhesion. Okay. And then as the water moves up the sides of the tube, then it's going to start bringing up the center of it to join. So the center comes up to move because it's attracted to all the water molecules along the side. Okay, so the water is following itself because of cohesion. Okay, so water follows itself for cohesion and then slides up the side for adhesion. Now we have a new level, and now the water can climb up the sides again. It's attracted because of adhesion. And then we bring up the level again because the water follows the other water molecules, and then it brings up the center. Okay, and what you're actually creating there, and again, this is terrible drawing, you're welcome, is your meniscus, right? The reason that there is this curvature here is because of the adhesive forces that are causing that little bit of attraction to the side. Now, if there wasn't this attraction to the side, then it wouldn't do this. It would do the opposite. In mercury, for instance, mercury has really high cohesion, but not so much adhesion, specifically with glass. So if I was looking at this for mercury, then it would look like this, right? I'd have this kind of rounded. And if you've ever played around with a mercury thermometer, you've seen this to be true, because this is the way that it looks on the inside of the tube. And here's your mercury, okay? All right. So, all this talk about liquids gives us new insight into gases. We spent a lot of time talking about ideal gases, and then we got into real gases briefly, and now we're going to kind of talk about what characteristics have to be true for a gas to be a real gas versus an ideal gas. So how closely can a gas mimic an ideal gas? So let's talk about vapor pressure a little bit more. If we're relating this back to our intermolecular forces, if we have a really strong attraction between a molecule and itself, then what do you think that's going to do to the vapor pressure? And remember, vapor pressure is caused when there is evaporation occurring. So if we have stronger intermolecular forces, is that going to increase or decrease my ability to evaporate? That's kind of the question there. And hopefully you're saying, well, if I have stronger attractive forces in my liquid, then I'm going to have a lower vapor pressure. Okay, it's going to be harder for me to evaporate because it takes more energy to break apart these attractions or stickiness between my water or my liquid molecules. Okay, so now if we're kind of relating this idea to gases, remember PV equals nRT? That was our ideal gas law, and we said that we had to have these two assumptions about gases. The first was that the particles themselves have no volume. So the V in our PV equals nRT is just the volume of the container. And the second one is that there's no IMFs. Now we have a term for it, right? At the time we just said, well, there's no attraction or repulsion between the particles, and that has something to do with the pressure, because the pressure is how much or how many times these particles are colliding with the sides of their container. So now we're saying, well, there's not any attraction between them. So if we wanted to think about whether or not gases act like ideal gases, then we have to account for these two assumptions. So if we're analyzing a gas and trying to figure out if it's more like an ideal gas or if it's something we'd have to use the van der Waals equation for, then we'd have to see whether or not the particles are close to having no volume. So that means that they're small, right? It's more like an ideal gas when particles are small. And again, particle here can mean either an atom or a molecule, right? If you have a big complicated structure that's a gas, then that's probably not going to fulfill that first assumption. And the second one then, it's going to act more like an ideal gas when you have lower intermolecular forces. If you have something in the gas phase that has a lot of attractive forces between it and whatever it's mixed with, or just it and itself, then that's going to cause an issue with the pressure up here, and it's going to act less like an ideal gas. So the fewer the attractive forces, the fewer the IMFs, the smaller the particles, the more like PV equals nRT is going to work out pretty well. Okay. So it looks like we need to find a way to determine what forces are present in a sample. So let's talk about determining IMFs. I always sit on my couch when I do these things, and my feet started going to sleep, so you should see the contortion I'm in right now to do this lecture just for you. Okay, determining IMFs. So let's take a sample, for instance, of ammonia. Remember, ammonia is NH3. So if we wanted to figure out what attractive forces are in a sample of ammonia, just ammonia mixed with itself, then we first have to draw the structure. Okay, so that would start with drawing the Lewis dot structure and then determining the VSEPR structure, and we would figure out that nitrogen likes to be a trigonal pyramid when it's attached to three things. So it looks like this, right? And then the second thing you have to do is figure out the polarity of the molecule. Okay, so if the molecule is polar, then that's going to mean that it can do dipole-dipole attraction. If it's a specific type of polar, then it could do a hydrogen bonding even. So we need to figure out the strength of the different attractive forces present. So if I go to my Pauling electronegativity scale here, and I'm looking up just the bond between nitrogen and hydrogen, which I'll put back into the context here in a second. Nitrogen is 3.0, hydrogen is 2.1. So you're already thinking, all right, it's a polar bond, and my nitrogen is more electronegative, so all the dipoles are going to point towards my nitrogen. And when I put those into my pyramid here, this one's going to point up towards the top, this one's going to point towards the top, this one's going to point towards the top, and if I was to combine them all together, then the net dipole for this thing would go right up through the middle and point that way, meaning that I have a slight negative charge up there and a slight positive charge down here. Now if I have another one of these guys, which I do because I have a whole solution of them, then it's going to do the same thing, right? I have a partial negative up here, partial positive down here, and it looks like there's going to be attraction then between these opposite charges on my adjacent molecules. So this attraction here, I have two polar molecules, so it's dipole-dipole, and I need to check to see if it's the specific type of dipole-dipole or hydrogen bonding. So it's a hydrogen, partially positive hydrogen on one with a partially negative nitrogen on the other. So if you go back to your notes, is that hydrogen bonding? And the answer is yes, it is. So we see that there's dipole-dipole there, we see that there's hydrogen bonding there, and there's also van der Waals, because van der Waals is in everything. Comparatively speaking, because it's the weakest of the attractive forces, it's sort of the least interesting thing about these two molecules together in terms of strength of attraction. But it's still one of the attractive forces that's present. Random motion of electrons is causing induced dipoles, even though there are already dipoles present on both of these guys. Okay, so this is how you determine IMFs. Let's look at another example. Let's take carbon dioxide, which hopefully we've played around with long enough to know the structure of. We know it's linear. Okay. So if I look to my Pauling electronegativity scale, if I'm looking at the difference between carbon and oxygen, carbon is 2.5, oxygen is 3.5. You could have probably guessed that it's polar even if you didn't remember. So it's going to have a dipole on it that looks like this. Now remember, when you put these in and you add them head to toe, then they're going to directly cancel each other out because they're at 180 degrees from each other, right? Because it's a linear molecule. So that means this molecule is non-polar. And in a sample of CO2, whether it's solid or liquid or gas, I mean more relevant in liquids and gases, then the attractive forces that are present are just going to be van der Waals. Only. Okay, and the reason that it's only van der Waals is because it's a non-polar molecule, right? There's only going to be induced dipoles on this thing, even though there's polar bonds. Okay, so that's the way that we determine these intermolecular forces. So hopefully this helps with some of your homework problems. If you have questions, let me know, and I'll talk to y'all soon.